Thank you very much, Fernando, for the kind introductions. So welcome everybody. Whether it's morning for you, afternoon or evening. So welcome to all for this presentation about sector-based energy efficiency. So the objective of this presentation is to get an overview. So 1 hour is relatively short time frame to handle such a complex and rich topic as energy efficiency in different sectors. But we'll try to identify the main strategies and the main potential that have been identified in several countries. So it's really to give an overview of what is possible and what are the main paths for action. So I will start with the industrial sector first. No particular reason, but industry is a big energy consumer, and we'll follow with the commercial and institutional sector, then end with the residential sectors presentations. So for the industrial sector, I think it's important to start with the big items. And in the industrial sector, energy consumptions, mortar is really one of the largest energy consumer and where there is also large energy potential. So globally, electric motors for industry consume about 25% of the electricity produced in industrialized economies. Oh, by the way, the presentation today will focus mainly on electrical energy, but some of the principles also can be applied to other type of energy, especially when we will talk about the building envelopes and systems. So back to mortars, they use, depending on the countries, if we look at the country or national energy consumption in the industrial electricity sectors, we find very often that mortars constitute 55 to 65, in some countries it's even up to 70% of the total electricity consumed in the industrial sector. So that's a huge amount of energy, and of course that's justified that we devote some time to understand what are the different end usage for motors and how we can curb the consumption and reduce it. So basically, motors are used for different applications like pumping system, fans, compressor. And here for compressor, we have different sub-applications. They can be used for compressed air productions, process. They can be used in refrigeration systems or air conditioning, so for space cooling, while refrigeration is more for lower temperature applications in the industries. They can be used for machining or for moving things around in the industries. So one of the observations that several of you are probably aware is that when we talk about motors, one of the biggest potential rely in the installation of variable speed drive. So especially if we are looking at the centrifugal type of equipment, so fans, pumps, and some type of compressor also fall into this category. So here we have a curve that just compare how the traditional throttling methods, so using damper or valve to reduce the flow as the need in the plant is reduced for a system, compare with a variable speed system. So variable speed system take into consideration the fan and pump law, and the power basically reduce, not exactly at the third power, but close to the third power of the flow. So that makes installation of VSD one of the most interesting applications. One of the big questions when we look at the potential for a given country is how many of the installed base of motors can be retrofit with variable speed application. And there's not so many global studies that have been done on these topics, but I illustrate here that some countries have made very in-depth research about motors. So the Department of Energy in US, for instance, have done a study in 2002, and one of the main findings was that between 18 and 25% of motor energy in the manufacturing sectors can benefit from variable speed drives. So that means about 1/4 to 1/5 of the motor energy consumption is potential target for the installation of variable speed drive. Of course, that was 2002. In 2014, one of the big question that we have when we start to evaluate potential in the market is how much of this potential is already achieved with installation of VSD, because VSD in the last 10 years has seen a very quick progression in the market. Another one is the improvement of industrial motors. I don't know if you have the same glitch with your slide that I see here for mine, but anyway, excuse for that. It was not in the original version. So for motor improvements, we can find on the market different category of motors. So there's obviously standard motors that are being phased out of some of the economies around the world, but they are still present in several others. There's the energy efficient category, and there's the premium efficiency, which correspond to IE3 in the European Union. What we can say about high efficiency or premium efficiency motor is their initial cost is slightly higher than standard efficiency motor, and that's because they use more advanced technology, and manufacturing is require more precision and better material. But this first cost is not really so important when we consider the life cycle cost of operating a motor system. So in several motor system studies has demonstrated that energy costs can be up to 97%, but typically we see several applications where energy cost over the life of the motor is 80% to 90% of the life cycle cost, including capital purchase of the motor initially, then operating costs. So what makes the premium efficiency motors different? So there's different characteristics that combine to give the higher efficiency. So those kind of motor use longer core. They use steel with better magnetic properties. The tolerance for manufacturing are better, so there's reduced thickness for the stator laminations. There's a reduced gap between the stator and the rotor, and all this contribute to achieving a higher efficiency. Of course, because there's a lot of Joule effect losses in motors, larger size conductors or using copper instead of aluminum are also ways that manufacturers use to increase the efficiency of their product. Then we can combine that with better insulation materials, high quality bearing, better lubricant, better designed fans and bearing system to reduce the mechanical loss. So all this make the high efficiency motors more efficient, not by a very high percentage. So generally it's fall between 1 and 4% of electricity reduction with the premium efficiency motors compared to standard efficiency motors. But this also, beside the energy efficiency gain, it brings also other benefits, like those motors are generally more reliable, they last longer, and they result in lower transformer load. So there's other side benefit to using those technology. So here we have a typical curve that despite the efficiency of different motors at different loading, and we see that generally, the general rule is that higher capacity motors maintain their efficiency at part load better than motors with a smaller or fractional horsepower or kilowatt. And we see that those motors, let's say, starting here in the 2015 to 25 horsepower, maintain their efficiency down to about 40% of loading, which is quite good. Of course, a smaller motor at 40% have already a significant loss in energy efficiency. So in order to evaluate the gain, there's different tools existing on the market that can help you, because obtaining curves from manufacturers, especially for existing motors that have been in place for 20 years, is always one of the challenge when doing a potential evaluation for a market or energy audit for a specific site. And I just present here one of the tools that could be used to make a quick analysis of motor improvement. So that's a screen extracted from RedScreen. So RedScreen is a free software offered by the Canadian government, and it can modelize complete buildings or also individual systems. So in this case, that's the input sheet for a simplified motor system. So we see that we have only a few parameters to give to the system. So what is the base case efficiency of the motors? So that's based on generic curves. So we just specify that the motor is standard efficiency in the base case, and it will be compared to a premium efficiency in the proposed case. The nominal power of the motor should be provided, and the system will propose from the generic curves what is the base case probable or most probable efficiency, 93.6 in this case, and what could be the proposed case for a premium efficiency motor. So that's the efficiency at nominal load or full load. Again, most motors are not working at maximum loading, so 75% could be a typical load factor for motors. So based on the 75% load factor, the system will also, using generic curves, propose an efficiency at this 75% loading. So the motor that was 93.6 as full load dropped here to 92.8. So this kind of quick tool can help engineers and market researchers to make a quick analysis of improvement potential for motors. Other points that we can mention about motors, so there's possibility to reduce energy consumption by avoid oversizing of motors, so making them run in inefficient zones, or undersizing of motor, which generally result in overheat and shorter life. In several industries, a motor management program has been put in place to ensure that the stock motors, the installed base of motor, are fully optimized, and that's a continuous process, so it's not only a one-time activity. Another point that is very important to understand is when we start to implement premium efficiency motors or even energy efficient motor in the market, we must be very careful about the repair practice that are used, because several studies have demonstrated that high efficiency motor that is repaired in a shop that doesn't use the best or the best practice and the appropriate equipment, you can lose up to 2% in efficiency reduction after non-optimum rewinding. If you apply, on the other hand, the best practice, you can achieve less than 1% reduction. In fact, last year we concluded a study where a Chinese laboratory even tested replacement of stock rotor of motors during a repair activity with copper winding core. And this allowed the motors to perform even better than what was its nominal efficiency before the repair. So in fact, with proper technology, it could be theoretically possible even to increase the efficiency of stock motor during repair practice to match or almost match the efficiency of new manufactured product. Other best practice are to keep the motor cool, clean air vents, balance the three-phase voltage, which can create overheat in the motors, and power factor corrections. And here there's two basic philosophy or approach. You can install the capacitor on the motor side, so that means you will benefit from reduction in amps distributed in the distribution system of the plant, or you can install it at the electrical entrance. So at this time you will correct for the utility, but it will change nothing about the power factors inside the plant, in the distribution system itself. Another big items in several industry is the compressed air system. So that's system that consume large quantity of energy. Depending on the industrial process, compressed air could be 5% up to 20-25% in some type of industry. And here also energy is a significant part of the life cycle cost for those type of systems. So it can reach easily 80% of the total life cycle cost, including compressor purchase and compressor and energy uh, required for the operation over the lifetime. There's also heat losses, important heat losses related to compressed air. In fact, in most systems, only 10% of the input electricity to those compressed air systems is effective in providing pressure and airflow to the final system in the plant. So there's different losses that accumulates, like generation in the compressor itself, treatment like desiccant or water removal, the distribution losses by frictions. There's several misuse in so many plants, so where compressed air are not used for really the best application. You can replace several applications by other types of motors. There's a significant portion of heat generated in the process of compressed air production and delivery. And finally, you find only a small fraction that is useful, uh, useful energy. So experience shows that reduction of air losses can very often correspond to 20 to 30% of total productions, and even in industrialized countries. So some years ago, we have done a study for a large utility in North America, and we did visit 150 plants, industrial plants, and we made measurements of the leakage during standby period of the plant operation. And we found that on average, on the 150 plant, 30% of the compressed air was going to feed leaks. So that's a huge amount of energy. In fact, the worst plant were close to 50-55% of the energy going to the compressed air system lost as leaks. So here there's an example that even a small 6.4 millimeter leak at 700 kPa, corresponding to 100 psig, correspond to 300 light bulbs 24 hours a day for the year. So that's quite significant in terms of energy losses. Other potential initiatives that you can implement to reduce compressed air energy are the distribution system modifications, so installing buffer tanks or increasing the size of pipe or installing a second pipe in parallel, optimization of distribution pressure, compressor control, compressor efficiency, of course, replacing compressor. So modern units like screw compressor can really, with variable speed drive, can really increase the efficiency of the baseline system by several percent points. And multiple stage compressor. Again, on the distribution side, draining system optimization could be really one of the places where there is significant leaks. So the draining device installed at different points of the distribution system. Air dryer optimization is another major aspect, especially for desiccant systems. So desiccant are vertical, you found very often in the plant a vertical cylinder containing desiccant agent, so that will absorb the humidity. And generally they come in pairs. So there's one cylinder that treats the outcoming stream from the compressor, while the other is going through what we call a regeneration cycle. So where compressed air that is preheated is sent to the second cylinder to remove the moisture from the desiccant agent and the desiccant material. And that's really is a huge energy consumer, because in most systems up to 15% of the output of the compressor can go into this regeneration cycle. And one of the key aspects is how you control the end of this cycle. Generally, it's based on the humidity content of the air at the exit of the cylinder under regeneration. And what we have found in so many industries that the control system, humidity control system, are always equipment that are dedicated and that needs frequent calibration. And in most industry that we have done, they were out of adjustment. I did mention that there is very often in industry usage where compressed air are applied to wrong end usages, like cleaning, which is really quite an expensive way to clean space and equipment. It's used also for cooling of components. It's used as a hair knife for oven and for dust removal. So that's another cleaning application. And what we have found in several industries, we can reduce by 90% the energy required for cleaning or dust removal application or hair knife by using other types of techniques, but not compressed air. If you have still to use some compressed air, it's very often interesting to consider using venturi nozzle instead of using system pressure to create nozzle and airflow. Next topic is the electricity transformation. So energy efficient transformer has been around for a long time. They are still penetrating slowly in the market. So that's transformer that can optimize the energy consumption by reducing two types of losses. So the first one is the joule losses, or it's called also the copper losses. And this one is proportional to the amount of current going through the transformer and the resistance. So again, this could be reduced by higher caliber of wiring or better conductivity of the material. The second aspect is the magnetic loss or iron losses. This one is function of frequency and voltage, and loss are experienced in the core as eddy current and hysteresis losses. So one of the solutions is to use better material. One of this material is what we call amorphous steel transformers. So that's a type of steel that has better permeability to magnetic field and effectively help to reduce the energy loss in transformer. Larger winding was already mentioned, and better tolerance, the same as in high efficiency motors. So in general, energy efficient transformer will give you a benefit of a few percentage savings. So it's not huge savings. In general, it could be difficult to justify replacement of a transformer in what we call a retrofit project. Retrofit means that the transformer is still good. You want to replace it before the end of its life, based mainly on the energy savings. So in most cases, it's preferable to consider the replacement of transformer by high efficiency transformer when you replace a unit at the end of its life or for new installations, for new units. At that time, the economics change completely because you don't have to consider the complete cost of the unit, but only the incremental cost, because you are in a context where you are going to purchase anyway a transformer, whether it's standard efficiency or high efficiency. So you just consider the incremental cost versus the energy savings to determine if it makes sense or not. Another point that could be interesting is the reduction of losses in the distribution system itself. So actually it's around 2% according to various studies that have been done. And upsizing the electric cable size have the potential to limit the losses to less than 1%. In fact, there is actually a regulation, or not a regulation, but a proposal for a regulation that is considered for the European Union, because it was found that the potential in the distribution system itself is more than what has been achieved for some products that are currently regulated with the minimum energy performance standard and labeling in this European jurisdictions. Next point could be the energy efficiency in the industrial process. And there you have as many process as you have type of industry. But typical situation is what you find in oven and furnace. So here I just kept the presentation a little bit more general by considering that this furnace can use either fuel, fossil fuel, or electricity. Of course, if it's a fuel, we can work on the combustion efficiency. But if it's electricity, of course, the efficiency will be 100%. But inside the oven, you can work generally on how the heat transfer is done between the source and the product. So generally, we rely on the three physical concept of conduction, convection, and radiation. And even if manufacturers are specialists in the development of their oven and product, we have found in several projects that it's not necessarily optimized. Very often, the design of oven is a part of engineering, but it's a part also of tradition, I would say, and experience. One of the projects that we have done recently was in a food plant, where they are just cooking meats, and they have purchased a brand new oven lines that have three different cells for cooking. And we were doing a study in this plants and monitoring the energy usage with the energy management system. And one day there was a breakdown in one of the cells, and the operator had to find a workaround to make the plant run without the damaged cell. So they were able to achieve cooking using only the two remaining elements or parts of the furnace or cell of the furnace. And that was interesting because we observed for that day and week of failure that the energy consumption went down by about 25% for this production line, maintaining the same output. So that just provided a hint that the furnace was not really designed optimally, because even with the workaround, operator were able to increase the efficiency. So we did work closely with the manufacturer. There was some issue about fire protection and other points that have to be considered, but we did change the design and how the conduction, convection, and radiation were used to transfer heat to the meat, and we were able in the end to reduce by about 15% the energy consumption of this particular plant. So there's definitely things that can be done on those kind of equipment. Heat containment or insulation is one of the strategy also that can be applied, and waste heat recovery. There's another one that is not mentioned here, but in several oven infiltrations at point of opening where the product enter and exit is something that needs to be closely looked at, because there's several opportunity for reduction in most oven working on those elements. Beside the furnace and oven itself, there's also enabling technology that can be used. So better sensors and process control, advanced material, and auxiliary system that can result in significant energy savings. And not only energy saving. I remember that for aluminum plant, one of the problem was the sensor was failing so rapidly in the molten aluminum that basically the oven was controlled manually, and it was overshooting very often the target temperature, which resulted in loss in productions for this plant. So it was possible to design a new sensor that was just intermittently intermittently measuring the molten aluminum temperature, then getting out of the molten aluminum. And this allowed us to resume an automatic operation without overshoot of the oven. And again, it was resulting in very large saving for the plant. Besides that, you have several applications now where advanced technology can be used. For instance, plasma torch are now used in different applications. In this case, for sludge oxidations. Mechanical vapor recompression also is something that you see very often in the market. It has been applied, for instance, in breweries where you recompress low pressure fumes from the kettle and use that steam at higher pressure and higher temperature as a preheat for the byproduct that will enter the kettle. Another application that we see also deploying quite rapidly in the industry is the industrial heat pump. And here we just illustrate that there are different sources at different temperature that can supply different needs or end usage. Monitoring and targeting is more on the management side, but it's one of the important potential. And there's still a lot of industry that doesn't do monitoring and targeting of energy consumption for their main process equipment, and there's definitively a large potential. So what we have found is that in most industry that apply those techniques seriously, I would say, with certain level of effort, they can generally find between 5 and 15% of energy reduction. So this is an example here where we have a plant that is monitored, and we separate clearly the hours of production in green, the hours for cleaning in blue, and the hours for standby operation, which is red here. And those kind of monitoring and targeting allow to detect interesting points, like during the cleaning cycle, that's really where you find the peak demand. So the plant operator and management was thinking that the boiler itself was the big energy consumer for the plant, but they found that the domestic water heater or the cleaning water heater was really what was causing the peak demand that was charged at very high rate in this particular country. Energy management and monitoring bring us to the next topic, which is the implementation of a more comprehensive ISO 50001 energy management system, which comprise, in addition to energy monitoring, the implementation of energy policies, the planning of a series of activities for aiming at reducing the energy consumptions, then the implementation and operations. And up to now, nothing new. So we have seen in a lot of companies, people doing quite well the planning, doing the implementation also. What's missing in most industry is the checking component. So monitoring, measurement and analysis, finding non-conformity in energy usage, and finding corrective actions and applying them, and doing internal audits of the energy management system that have been implemented. So that's really the part of the loop that is missing in most industry, even if they are doing some of the activities that we find here in terms of planning. Again, ISO 50001 has the potential to reduce the energy consumption, and here we see very different penetration of those energy management principles in different part of the world. Like in Europe, it's relatively popular, ISO 50001. In North America, there's a strong reluctance of corporation to implement the full energy management system. Basically, they prefer to go, most of them prefer to go with a simplified approach. But still, you find some industry that will be willing to implement the whole process. But I think there's still a lot of education to do and demonstration in North America and in Asian country also. So this concludes the industrial sector. So let's talk a little bit about the commercial sectors, and let's start with the building envelope and what we call now the bioclimatic architecture. So, of course, building envelope is a bit difficult to justify on a retrofit project. If it's just to replace window or install new walls, insulations, and roof insulation, and try to get a very short payback from those activities, it's generally not the case. It takes generally longer investment to implement those kind of projects. But it's envelope optimization are activities that are perfectly well suited for large renovation projects and also for new constructions. And you see that one of the principles that is applied is to try to optimize as much as possible the natural resource. So in this case here, we want to avoid part of the sun energy during the summer when the sun is higher on the horizon, and we want to maximize the sun or the solar heat gain during the winter period. You can also proceed with natural infiltration approach to this kind of project. Here we have an example, which is the Federal Center South Building, which is a renovation of a very old structure, and it was done in a way that this building now is one of the most efficient one in North America. And this is by a combination of different features like the implementation of high-performance glazing on the facade, the orientation-specific louver, so what you find here. So the louver both reduce the heat gain during the summer period, but also they reflect part of the sun lighting on the ceiling of the room, so to favorize the natural lighting. So you have also low temperature distribution, hydronic systems. You have low pressure underfloor distribution system of air, so you use natural convections, in fact, to ventilate the building. So it's not the high pressure from ventilators that move the air mainly. It's the natural convection, so the air picking up warmth and raising gradually and getting out by these louver here at the top. Other points that are quite interesting is that they integrated hydronic loops for hydronic system inside the pile. So that means you already have to dig holes here or to install those piles. And by combining the hydronic system in the pile, you reduce significantly the cost of implementation for those components. Eutectic storage for phase change material, so you can stock some cooling during the warm season or heating during the cool season. And you have also light pipe. So that's different feature that can be implemented in a system in a bioclimatic approach, meaning that you want to use as much the natural energy and the site specificity and weather to optimize energy consumption. So this is another example, one building that I visited last year in Singapore. So you have the combination of natural lighting using light pipes. So that's collector here outside of the building that will bring the light inside the middle of the rooms through a mirror-coated duct. There's a shading device. Again, the shading device are to reduce the heat gain during the summer period, but at the same time, they reflect part of the sun lighting to the ceiling of the rooms in order to reduce the artificial lighting. There's integration of renewable on the roof, and this one that is maybe more debatable, but that was an experiment of using very small diffuser. So each workspace has its own control for ventilation, so they can increase or reduce the ventilation, a little bit like what we find in airplanes. So is a bioclimatic approach really new or something that we just rediscover? It's always interesting to see that the first air conditioning system from Carrier was installed in the building in 1902, so that's 100 years. But before that, the architect and technicians have to look at the weather specificity of each site. So we have find a structure like a wind catcher here to do natural ventilations from the ancient Egypt. We find them also in Iran and Bahrain and Yemen also in the city of Sana'a. Other things that we see that are interesting are what we call biomimicry. So it's going one step further than bioclimatic. Bioclimatic is just looking at the specificity of the site to use natural energy, but biomimicry is going the step further by observing how natural living being has solved the temperature and humidity problem. So typical example is the termite mound. So where the termites were able to maintain by temperature inside the mound by 1 degree Celsius year round, even if the environment changed from 3 to 42 degrees Celsius. So there was one building built in Tanzania using those principles to try to reduce as much as possible by combining mass and natural ventilation, the requirement for artificial energy consumption. In terms of HVAC, there's a large quantity of options for energy conservation. So basically, we look very often at controls. Can we do a temperature setup, looking at the distribution temperature or the pressure of the distribution duct for ventilation system. Thermal storage offer a lot of opportunity, and I think it's still something that is not enough used in most applications, because we see that in several countries right now the price for air conditioning system is dropping rapidly, and the price, not the price, but the living standard are increasing also rapidly. So the combination of the two factors make the AC load is just booming in several countries, and that drives the implementation of the peak demand system for most countries. So in the Arab states in the last few years, the increase in demand was 9% per year, while the energy increase was just 6%. So thermal storage offers a huge opportunity, but the problem is very often that there's no incentive in the rate structure. And that's definitively something that needs to be looked at closely in most countries. Evaporative cooling in some countries where you have access to water, of course. Absorption unit, geothermal energy, free cooling, heat pumps. Again, on the heating side, you can look at control system, heat recovery, energy type replacement, radiant heating, and off-peak energy optimization. Again, you can use thermal storage to reduce energy usage on the long term. Another application is heat recovery that has been applied with success in different buildings, and there's different type of technology available. The simple run-around coil, so it's two coil with glycol systems that circulate glycol between the two coils. This one is especially interesting in retrofit application when you don't have proximity between the exhaust air and the inlet air. So with this kind of system, it's almost irrelevant where are located the ventilation system. You can install heat recovery system. Their main disadvantage is that they are not so efficient. Other systems that are popular are heat pipe, heat wheels, and plates. So what we see most nowadays are mainly heat wheels, because some of them have the possibility to implement not only the sensible heat recovery, but also latent. So here there's one figure missing, but this one should be around 85%. So with the latent heat recovery, heat wheels can achieve up to 85, somewhere also, sometimes a little bit more, 87% heat recovery. In HVAC system, there's mainly 4 energy strategy for centrifugal equipment. So here I will present fan, but pump operation are quite similar. So first you can work directly on the fan or pump efficiency. And we have on the square here a representation of different various type of centrifugal fan that can be found in the market. So this one is the less efficient, so that's the radial one. Efficiency of around 50% of 60%, meaning that only 50% to 60% of the energy is transformed to pressure and flow. The rest is lost in heat generation here because of eddy current in the flow in the fan. So this one is used mainly for harsh environment. Second one is in terms of efficiency is the forward curve blade. So the names imply here that the blades are curved in the direction of the airflow. You can achieve 60 to 70% efficiency. So these systems are popular because of their cost of manufacturing. So they are quite inexpensive and they target small HVAC. The one that we find the most in large building is the backward inclined fan. So you can achieve 75% to 80% and you can generate relatively high pressure using those systems. In a very high efficiency building, you will find a airfoil design. So that's fan where you will use blade shaped blade to reduce the losses and increase the efficiency of the fan. So you can achieve 80 to 85%. In fact, there's one fan that is not depicted here that have even a higher efficiency, and that's the axial fan. So axial fan could be very, very efficient. They can reach close to 90% efficiency. Their main problem is the sound attenuation because they are more noisy and in a higher frequency. But I have seen some very large building which were using axial fans with success. Other strategy, reduction of hours of operations, flow reduction and pressure reductions, which are quite popular. Artificial lighting is another big consumer. In most buildings, it's 20% to 40% of total building stock energy consumption. So in office building, typically we see in several countries 40%. Of course, it depends what is the quantity of energy going to cooling and other type of end usage, but that's typical. And what we can say is that artificial lighting is still very inefficient. For instance, incandescent system generate almost 95% heat from the input electricity. And there's a large quantity of loss that accumulates. For instance, the electric to light conversion is the first one and most of the time the largest one. So this diagram is not to scale, it's just to represent the different losses. Then you have fixture losses, so that means lumens that have been emitted by the lamps but captured by the fixture itself. There's the rooms losses, so again, photon or lumens that have been emitted by the lamps that get through the fixtures and that are absorbed by walls, ceilings, or fixture, not fixture, but furniture in the rooms. Then you have other types of losses, which means that the useful illumination is relatively a small portion of the total input. In terms of lighting opportunities, so most people are probably aware of this simple approach. So use more efficient fixture, lamps, ballast, reflector, and lamps. So it's generally you have to consider the four components individually and as a system to achieve the highest efficiency for your lighting system. Use of timer, automatic dimming, occupancy sensors. The natural daylights are becoming very popular, so how to favorize daylights to reduce the artificial lighting near the windows, especially, or using light pipes. You can even make the daylight penetrates deep inside the buildings, but it's still relatively expensive for those kind of applications. Task lighting and using lower general lighting level has been applied in several buildings with success. Reduce excess lighting by delamping, mainly retrofit applications. Occupant awareness, turning off lights. This one is something that is not a single activities. You need to repeat those kind of awareness activities from time to time to maintain the motivation of people to participate in such program. Maintain and clean regularly the system, select interior surface and color for diffuse reflections, of course, when you repaint. In terms of building envelope, the principles are quite similar to what we have seen for the commercial building, except that the infiltration is generally a largest component for housing. There's generally a higher percentage of energy losses going through infiltration than what we find in larger size building. So first objective will be to minimize the infiltrations. At some point, we will find that in most buildings, we will need at some point to rely on artificial ventilation and heat exchanger to reduce the energy usage, but while maintaining a minimum external air input for health purpose, oxygenation and dilution of air. Insulation, of course, very traditional measures, and orientation. Orientation is again one of the way playing with orientation and shading device, like we see here, to shade the summer heat gain, using advanced like triple windows on the north side or low E or argon fill window, using thermal mass also to stabilize the heat gain or spread them for during the day. Can be other options here. In terms of lighting, of course, the light source is one of the important elements to consider. So there's different source available to designer. One of the oldest one and one of the most inefficient one, by the way, is the incandescence. We reach an efficiency of 10 to 18 lumens per watt with a very short lifetime of 1,000 hours. So main advantage is it's an excellent color rendering, and it's very inexpensive. So that makes the incandescent lamp still used a lot. But it's decreasing even in the development country. In fact, last week I was in Africa, in Benin, which is a relatively poor countries, and a survey that have been done shows that the penetration of CFL over incandescent is more than 50%. So it's close to 60, 65%, and even 80% in the middle class. So incandescent is phasing out rapidly in most countries. And in fact, several governments are just banning those kind of lamps to get them out of the way the most rapidly as possible. But still, a lot of applications in the residential sector, especially in Europe and North America, use halogen lamps. And halogen lamps are not much better than incandescent lamps. They have a relatively higher lifetime, excellent color rendering, but and they are quite popular. And before the introduction of LED lamps, there was no easy replacement because compact fluorescent lamp generally cannot fit in the halogen fixture. So that's still one of the big potential and the big opportunity that remains in the lighting for residential sector. So replacing all those halogen lamps by LED lamps. Compact fluorescence, so becoming the main trend in most countries. And this also is starting to lose market share compared to LED lamps. So LED lamps are LED, in fact, are still quite expensive, so that makes their penetration relatively slow, but they are gaining market share in most countries relatively rapidly. Next potential that can be found is the appliances. And here several governments are acting, so I think there's now 60 or close to 70 countries that have applied many minimum energy performance standards. So for different products, some countries have just one product enacted, and some other countries have dozens of products that are covered by those standards. and there is also labeling standard. So whether it is endorsement standard like Energy Star or comparative standard like the European Union label here, or the STAR system that we found in several Asian countries, those systems have been found to be very effective. In fact, in terms of cost for the implementation of minimum energy performance standard and labeling system, the design and preparation work for implementing those kind of regulation are just a fraction of the saving that could be experienced by a country by implementing those options. The main problem in all those problems is the enforcement, which is very weak in several of the countries that have implemented the label. So the label are not necessarily respected. So a country that decides to go that path, going to minimum energy performance standard and label, should be really serious about enforcement and market supervision and monitoring. What is interesting about this approach is that it could cover several types of appliances. So air conditioning is very popular, refrigerator, a freezer, television set, dishwasher, washing machine, dryers, and so and so. And we see here on the right how the different regulations and program can combine to transform the market. So you have this curve, which is the normal market curve before the introduction of any energy efficiency initiative. So you see a distribution of product from the less efficient here to the most efficient following a statistical normal curve. If you implement a minimum energy performance standard, so you draw lines to the minimum performance of equipment that can be bring in the market, and you immediately transform the market to this curve here. So after implementation of minimum efficiency standard, then you can still improve the market by adding a labeling. So the labeling will try to bring the curve further to the right, and you can also add incentive programs. So incentive program can still mix with the regulations, but in this case you will incentive only product that have a very significant energy efficiency gain over the minimum energy performance standard. So let's say you will just incentive product that are 3 or 4 class over the minimum class, or 20% or 30% better than the minimum energy performance requirements. Standby power or shadow or ghost energy usage. So that's one of the large energy consumer in the residential sector. So the current figure in North America is about 5%. So 5% of the energy in the residential sector electricity is going to standby power. So that's equipment that just, as we say, blink in the dark and produce nothing useful. In some country where there's less standby regulation implemented, we have seen figure up to 10% and even 12% of the energy consumption in the residential sector. So standby power is definitively something that should be considered if you want to optimize energy consumption in the residential sector. So again, electricity distribution, the same principle as was discussed for the industrial sector, also apply in the residential sectors. And again, there is a strong lobby that is done actually in different jurisdictions to adopt higher requirement for wire size in order to reduce energy consumption in residential stock. Last topic is the HVAC for residential sector, and this one is quite important in several regions around the world. I already mentioned the Middle East, where there is really a surge of installation of small AC system in household and apartment, and the same trend has been observed also in several countries in Southeast Asia. So again, price of manufacturer and retail price of AC unit are going down, and the living standard and the earning of the families in several countries are going up. So there's really a very large adoption and penetration of those equipment. So this study has been done a few years ago to look at AC equipment efficiency in different jurisdictions. So I just show here the result for the European Union, but similar studies were done in 8 large economies, including North America and several countries in Asia also. So we see here that the efficiency, what we call the project weighted average EER, so that's the average EER of all product on the market, but weighted according to their sales, so the popularity of the equipment. So the equipment that are more popular are weighted higher in this average. And we see that over the years, between 2002 and 2011, there was almost a 25% gain in efficiency on the average split air conditioner sold in the market. But that doesn't mean that we have achieved the maximum potential, because in the same study, we were looking at the minimum efficiency found in each market. So here in Europe, it was almost 2.2 watt or watt per watts, or cooling watts per electricity watts, with the average at 3.2. But the EER of best product in the market was much higher. So there was a huge gap or potential remaining in several markets. And here we see that in Europe there was unit in the market at 5.6, while the average was 3.2. So it's not the double the efficiency, but it's almost close. So combine that with the huge increase in penetration of air conditioning equipment, I think that's one of the largest potential untapped actually in several countries. And a lot of countries are moving rapidly, either by introducing minimum energy performance standard and labeling program for air conditioner, but also by providing subsidies to transform the market toward those equipment with higher energy efficiency. So they will be manufactured in a larger quantity, which will bring down the price eventually in the future. And the last slide is the same information, but for unitary air conditioners, so window units or through-the-wall units, which generally are slightly lower in efficiency. And basically those units are becoming less and less popular because the split system are becoming really the main seller in the market. So most of the market studies done in the last few years shows that the window units penetration or popularity are decreasing while the split is increasing. But and we see also that potential for window unit is much lower in several jurisdictions, including European Union. So that makes some country like Saudi Arabia right now is considering the implementation of MEPS for split system and window unit, but at the same time they consider banning altogether the window unit because the potential for improvement of those kind of units are always lower, and they want to ensure the maximum potential. So that was all for this presentation, for this quick overview, trying to pack in 1 hour an overview of the different techniques and opportunity that we can find in different markets when we consider the implementation of energy efficiency programs or initiatives. So thanks a lot for listening, and Fernando, floor is yours.